Last time we derived a formula for the 3 dB bandwidth of a non-inverting op-amp amplifier in terms of the gain bandwidth product of that op-amp. This time we're going to derive the equivalent formula for an inverting op-amp amplifier and have a quick look at summing and differential amplifiers as well. Okay, this is a simple inverting amplifier, and we're going to start the analysis the same way we did when we were analysing it at low frequencies. We're going to look at the current through R1 and the current through R2. Now, applying Ohm's law to Vin would give us that Vin minus the voltage on the inverting input here, which I'll just call V minus, over R1, that's the current flowing through this resistor here. I can no longer assume that V minus is equal to 0, as I did before when we were assuming that the open loop gain was effectively infinite. This current has got to be equal to the current flowing through R2 as well, because we're still assuming that the op-amp is ideal in the sense that there are no input currents flowing into its inputs. So the current through R1, this must be the current through R2, and the current through R2 by Ohm's law will be V minus V out over R2. And we also have, for the op-amp itself, that V out will be its open loop gain times the difference between its two inputs. Well, its non-inverting input is at 0, its inverting input is V minus, so that would just give us V out equals minus A times V minus, or V minus equals minus V out over A. And once I know that, I can substitute this into these terms and eliminate V minus from our equations. And that would give me that V in over R1 minus V minus is plus V out over A, so that would be plus V out over A times R1 equals V minus over R2 is minus V out over A R2 minus just V out over R2. Collecting all the V out terms on this side and the V in term on that side would give me that V out 1 over A R1 plus 1 over A R2 plus 1 over R2 is equal to minus V in over R1, and that gives me the frequency response, or the V out over V in, as being minus 1 over R1 over 1 over A R1 plus 1 over A R2 plus 1 over R2. And if I multiply everything by R2, that would give me minus R2 over R1 over 1 plus 1 over A plus R2 over A R1. And I've done that because minus R2 over R1, that is the gain of this amplifier at DC, at low frequencies. That's the formula that we've calculated before for the gain of an inverting amplifier. So I could just write that as the gain at DC minus R2 over R1 divided by. And if I'm going to proceed any further, I'm going to need to be able to express A in terms of its frequency-dependent form. That A is the open loop gain at DC divided by 1 plus J F over Fd, the characteristic frequency of the op-amp where the gain starts to decrease. That gives me 1 plus J F over Fd over ADC plus R2 over R1 times 1 plus J F over FD over ADC. And expanding these terms a little gives me GDC over 1 plus 1 over ADC plus JF over ADC times FD plus R2 over R1 times 1 over ADC plus R2 over R1 times JF over ADC times FD. Now, ADC is a huge number, hundreds of thousands. So 1 over ADC will be negligible compared to the 1, we can neglect it. R2 over R1 will be the modulus of the gain of the amplifier. It's not going to be more than about 100 or so in most cases. So if I take that 100 and divide it by hundreds of thousands, this term is going to be negligible as well. That just leaves us with this. The gain at DC divided by 1 plus J F over ADC FD 1 plus R2 over R1. And as we've seen before, ADC times FD is usually known as the gain bandwidth product of the op-amp. So I could write this as GDC over 1 plus JF over the gain bandwidth product of the op-amp times 1 plus R2 over R1. And compare that to the form of the frequency response that we've seen before. The gain at DC divided by 1 plus JF over FB, where this is the 3 dB bandwidth, shows that in this case, for an inverting amplifier, the 3 dB bandwidth is equal to the gain bandwidth product divided by 1 plus R2 over R1, which is usually written as the gain bandwidth product divided by 1 plus the modulus of the gain at DC. The gain at DC is actually minus R2 over R1, so the modulus of the gain is plus R2 over R1. And we get this formula here. It's subtly different from the formula that we got for the non-inverting case. It's got an extra 1 on the bottom. And you have to take the modulus of the gain at DC because the gain at DC is otherwise negative. And having a negative 3 dB bandwidth doesn't make much sense. I don't really have time here to go through the corresponding case for summing amplifiers. The algebra gets a bit tedious. For details, if you're interested, have a look at the short introduction to op-amp amplifiers document. It is different from the case of the inverting amplifier, and it's different in a very interesting way once you go through all of the algebra. Because you'll find that for a summing amplifier with any number of inputs, the bandwidth of the amplifier from any input to the output is always the same. It doesn't matter if the two input resistors are different. R1, R2, these could be different values of resistance. The bandwidth from the inputs to the outputs is always given by this formula here. The gain bandwidth product divided by 1 plus the sum of the modulus of all of the gains. So in this case here, with two inputs, one of which has a gain of RF over R1 times minus 1, and the other one has a gain of RF over R2 times minus 1. The modulus of those two would be RF over R1 plus RF over R2, and we would just end up with a 3 dB bandwidth, which was the gain bandwidth product of the op-amp divided by 1 plus RF over R1 plus RF over R2. And if you had more inputs coming into your summing amplifier, you'd just have more terms down there. It's different from a normal inverting amplifier because if you think about it in terms of superposition, supposing we only had one input that was actually being driven by a signal, we would ground the second input here. And unlike at DC, this resistance R2 now plays a part in the circuit because V-, the voltage on the inverting input here, is no longer ground. So you do have a current through R1, but you also have a current flowing through R2 from ground to the inverting input here, which is no longer at 0 volts. And we really do have to apply Kirchhoff's current law to this node here and take into account all of these three currents when we're trying to solve for our output. Differential amplifiers are interesting because you really can apply superposition here, and if you do, you'll find that the bandwidth from both of the two inputs is the same. If I just consider the 1 volt input here and ask what is the bandwidth from this input to the output, then I could consider it to be an inverting amplifier and write the 3 dB bandwidth as the gain bandwidth product of the op-amp divided by 1 plus the modulus of the inverting gain, which in this case would be 3 divided by 1 or just 3. So I would end up with the gain bandwidth product divided by 4. For the non-inverting input here, the 3 dB bandwidth is given by the equation for a non-inverting amplifier, and that would be the gain bandwidth product divided by the gain. Not 1 plus the gain, just divided by the gain. But for a non-inverting amplifier, the formula for the gain is 1 plus the feedback resistor divided by this resistor to ground. So it would be 1 plus 30 divided by 10, or 1 plus 3 again, and it would be exactly the same result. So we have the fortunate result that for a differential amplifier, the bandwidth of both inputs is the same. Next time, in the final one of these little videos, I'll introduce the concept of the X dB bandwidth and show how to calculate the X dB bandwidth from the 3 dB bandwidth.